Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'll announce you since Henry's not here. Jonathan Ullman, from all the way 2 T-stops away, is going to be giving a talk on PCPs and the hardness of private synthetic data.
Okay, thank you very much. I'm very excited to be speaking to this audience. It's really exciting for me. So the title of the talk is Probabilistically Checkable Proofs and the Hardness of Private Synthetic Data. It's joint work with my advisor, Salil Vadhan, who I can't wait to embarrass when he shows up late. And so what I'm going to talk about, no, not yet. So what I'm going to talk about is essentially the computational complexity of a certain kind of private data analysis. And in this work, we're going to look at connections between cryptographic unforgeability and the hardness of approximation and a certain type of data sanitization. So what's kind of the setting that we're looking at? You have a statistical database. It consists of the information of a bunch of individuals. And there are lots of useful sort of global properties of populations we'd like to learn from this data. But it's very important to the individuals that we don't reveal too much about their data. But unfortunately, there are malicious parties who might be able to infer properties about the individuals from the global properties we learn. So we're going to put it behind some sort of sanitizer that's going to let people interact with the database. They're going to send queries. They're going to get answers. And we should we? Oh, okay. It's a little red, yeah. They're not that malicious. Okay, this is very soothing. It's nice.
Yes, very soon.
Okay, much better. So the things we want from the sanitizer, we want that it be private. It protects the information about the individuals, but still gives useful answers to the queries. And for this talk, what we're interested in whether we can do that, but also have the sanitizer be efficient. So in the setting that I've kind of sketched out here, you have this interactive process where you keep the database around. And there's Salil, just in time to be embarrassed, as I said. So you have this interactive setting where you keep the data around and you serve queries to people as they come in. And in this setting, there's some reasonable techniques we know that seem decently practical. But we might want to be somewhat more ambitious. We want to take in a bunch of queries. We want to take in sort of a set that we think basically covers what we want to know, and we want to produce some kind of summary of the data. And then we want to throw it away. We don't want to have to worry about keeping it around. We don't have to worry about what's going to happen in the future. And this is sort of the setting we're going to focus on today, where there are techniques that are known. In fact, pretty surprising things are possible in this setting for achieving these private summarizations. But the computational complexity becomes a big issue.
Now, is it online, or is it so you have the full database sanitized and then throw it away, or do you get your data one by one?
You have the data all at once. So we've, for instance, think of the census. They collect the data once a year. They want to do something, and then they want to.
So you can keep making queries after you've thrown the database.
So the idea is that you have this summary that we sort of guarantee can act like the database, at least with respect to certain types of things.
But only for the queries which you created the summary.
Oh, that's what I'm asking. So the summary is created in response to
Yes.
the queries.
Yes, so the summary is created to preserve the properties, to essentially preserve the answers to the queries, and hopefully you've chosen your queries to be very general. So this is one of the reasons why this is sort of harder. You have to anticipate a very large class of questions people might want to know if you're going to do this.
So the sanitized database should support
all queries, and the summary is only with respect to a subset of the queries. So what's the difference between the sanitized database and the summary? How should we think?
So in particular in this talk, the summary is actually going to be a new database. We're going to somehow randomly generate a new set of data that doesn't reveal too much information about any real person in the original data. So it's what's called a synthetic database, and I'm going to define it more formally.
Oh, the sanitizer is an algorithm. Oh,
so the sanitizer is an algorithm. They should get different color coding or something.
I got confused.
Yeah, sorry. So the sanitizer is an algorithm that produces the summary.
Good. Okay.
And we want to run it once and throw the data out.
Thanks.
So, in general, so I'm going to start by introducing some concepts just to explain sort of results that exist in the literature for what we can achieve, and explain what some positive results we know about that are not computationally efficient, and then I'm going to present some new negative results for a fairly general type of these summarizations, in particular the ones I just described, where the summarization is itself a new database. And I guess what sort of I'm going to go through the summary maybe quickly, but I want to sort of contrast the difference between what we can do efficiently and what we can do inefficiently, and what we can do interactively and non-interactively. So in the negative results I'm going to present, in particular, are going to show that even if the type of queries we want to preserve the answer to is very simple and very natural, and one that's actually used by statisticians frequently, then efficient algorithms can't produce an accurate private summary. And we're going to see this by a connection that was developed in some earlier work of Dwork et al. Between digital signatures and data sanitization. And then we're going to apply the property of the local checking property of PCPs to get hardness results that rule out sort of simple natural queries. And if we get to it, talk about some sort of generalizations and some new stuff. So the first concept that I want to introduce is differential privacy. So the exact details won't be so important because our results don't strictly apply to differential privacy, but I want to introduce it to make a contrast between what very strong guarantees we can give if we don't worry about efficiency versus what we can do with efficient sanitization. Sorry.
It applies to a much...
Yes, sorry, our results apply to a much broader class of sanitizers, not only to those that are differentially private. So this has become a very well-studied notion in the computer science literature. It's due to a long line of work, sort of, I believe it's first introduced as it is in the work of Dwork, McSherry, Nissim, and Smith. So the idea is that we want to say that the output of the sanitizer doesn't depend substantially on any specific person's data. And the way we're going to formally guarantee that property is you imagine we have two databases that are neighbors in the sense that every person's data is the same except for yours. So if you can see it, X2 has changed his data, but everyone else is the same. And it can be changed arbitrarily. So for example, it could just change it to all zeros. It could just say I'm not in the database. And the sanitizer is we say epsilon differentially private if for every such neighboring databases and every possible outcome that the sanitizer could produce, the probability of this outcome differs only by a small multiplicative factor, like 1 plus epsilon, or for technical reasons, e to the epsilon. And epsilon we think of as something like 1/10 or 1 over 801 if you're Salil. I'll let him explain. But not something like cryptographically small, some sort of modestly sized parameter. And in particular, this notion is interesting because it's extremely strong. It doesn't make any assumptions about what is known by the attacker. So it's completely agnostic to the side information held by the attacker. It also has a particularly nice property that it's composable, which is not satisfied by many other definitions. So running if you run two sanitizers that are each epsilon differentially private, then when combined, they're 2 epsilon differentially private. So, they said, so this is, I don't want to spend too much time, advocating for this notion, although I think it's very good, but I think what's striking is that this is a very strong sort of gold standard definition of privacy, And in itself, at least statistically, it's consistent with doing some very rich summarizations of the data. So what kind of rich summarizations am I talking about? We have to somehow define, we have to consider a type of query that we're interested in preserving. And the kind that we're going to be interested in are called counting queries, or I may sometimes say predicate queries. I'll try to stick to counting. So suppose our data is just a set of binary attributes for each individual. In this case, there's 4 individuals, and they've given us 3 binary attributes about themselves. So a counting query is defined by a predicate on rows, so a predicate on a specific individual's data. And in my example, the predicate is whether you're both a smoker and have a heart murmur. I don't know why. So the answer of the counting query on the database is just the fraction of participants in the database who satisfy the predicate. So on the right, you can see the predicate applied to each of the rows. Only one person satisfies the predicate out of 4, so the answer is 1/4. So this is the only type of specific query we're going to consider for the talk. There's other things you could ask, but this is very popular. This is sort of a popular way of doing machine learning, for instance. And I'll briefly explain how this relates to the kind of thing that people want to do in the census. So how can we answer one of these with differential privacy? We use sort of the mother of all differentially private sanitizers. It's the Laplace mechanism. And this is very simple. Someone comes in with a counting query. They tell me a predicate. And what I give them is I give them the answer of that predicate query on the database, but with some noise added to it. In particular, it's noise added from this special kind of distribution called the Laplace distribution, which is just a symmetric sort of double exponential distribution. So it's a distribution with thin tails. It's symmetric, and it's given by this parameter. So I think I'm going to even skip the argument for why this is differentially private, but the important thing is sort of to quantitatively see how much noise we have to add to get differential privacy. And it turns out for one query, the noise is approximately 1 over n times epsilon. So this, just to kind of go through like the direction. So as n gets large, the number of people in the database gets larger. It becomes easier to protect one person's data. As epsilon gets smaller, we provide more privacy, so we add more noise. But of course, we don't just want to answer one counting query. We want to answer many. So if we're going to get m counting queries over the lifetime of the database, we have to add we can add independent noise from the Laplace distribution. So each time a query comes in, I sample I generate a new sample. I add noise to the answer of the queries. And in particular, for m queries, the standard deviation of the noise is going to be roughly m over n epsilon. It's not at all clear that the noise has to be independent. But when you try to do things that are not independent, this is where the complexity becomes a problem. So this is the mechanism, and this can be done efficiently and adds noise that's growing linearly in the number of queries. But we can also, if the database is much larger than m over epsilon, we can get arbitrarily good accuracy. And as I said, it's efficient in the sense that it runs in time polynomial in the size of the database and the number of queries.
Decreases inversely in n, where n is the number of elements.
This is the number of people in the database.
Even though the output to the counting query may be a very small value. So
Yes. This is an additive error. Yes. Right. So
how do I avoid, if it's additive, what if I just multiply by my answer? I sort of put a query in which I multiply by 1 over epsilon.
You multiply by 1 over epsilon, then the noise is also... I'm only telling you the answer and the...
So within.
No, but your error is additive. So how does I could then violate privacy by just multiplying the answer by 1,000,000, so effectively washing out your noise?
So I specifically said that the answer is to the counting query is a fraction.
Oh, I see.
If it were the actual count, then you would add n times this much noise. So now I just want to talk about one type of. Right. So I just want to very briefly explain a particular type of counting query we're interested in. I'm going to skip over the sort of pictographic representation, but in particular, a very natural class of counting queries that's generated a lot of interest, both in computer science and also in statistics, are counting queries where the predicates are conjunctions of some of the literals. So in particular, we're going to be interested in these k-literal conjunctions, and just for those who are familiar with this corresponds to a very popular method in statistics called the k-way contingency table. So in particular, when we use this mechanism, if we use the mechanism I described, and we want to answer k-literal conjunctions, then the number of queries we have to answer is growing exponentially in k. So for instance, if we think that our summary of the data should be should be that the new database preserves all of these queries up to maybe k equals 10, or even something depending on d, so preserves the marginal distribution of up to half of the attributes even, then this becomes very prohibitive. Yes, sorry, so d is the number of attributes, and I'm looking at the conjunctions of k of them. So I'm looking at essentially the marginal distribution of subsets of k attributes. So for constant k, this is efficient, although for large k, this is not necessarily practical, and the noise is also prohibitively growing in k. So if we want to do some sort of summary, we're going to need to be able to do something more intelligent than independent noise. So let's say we decide we want to answer all the conjunction queries of size k, and we want to produce some summary. So, yes?
How should you
I'm
think
sorry.
about D and then? What's the relation between them? Like D should be as large as
Constant?
n, or D is a
So
constant?
d is the number of attributes that your study looks at. So in some sense, d is like the amount of information collected in the study.
I understand.
So I'm not thinking of it as constant. I'm thinking of it as growing, and I'm interested in how the running time of the algorithm scales with d. But
Should I think about D as being n log n square root of n, or n squared?
so I think of d as being specified, and so if so for instance, d is specified by the study, and the set of queries you're interested in is specified by the study. So maybe I want to ask d squared queries. I want to know all the two literal conjunctions. Then in order to get sort of meaningful error, I have to make n be much larger than d squared. So what we're interested in is algorithms that allow you to get fewer samples, because we think of that as being expensive to do. So we want to produce some kind of summary, and I alluded to earlier in the talk that the kind of summary we might want to produce is what's called a synthetic database. We take in a collection of queries, and we produce a new database that has the same attributes. So if our original database had 5 binary attributes per person, our new database is also 5 binary attributes per person, but the rows are generated randomly. But they have this accuracy guarantee that for every query we're interested in, the difference between the answer of that query on the synthetic database and the answer of that query on the original database is at most some parameter alpha.
So you're somehow, when you generate the synthetic database, you're keeping the correlations in there.
Yes. So yes. So the idea is I want to preserve the
or
marginal
these
distributions.
correlations up to the size that you'll be querying.
How
Yes.
large is f with respect to n?
With respect to n.
Yeah.
So that depends in some sense on the algorithms. Like I said, so I think of it as we have a d attribute database, and we want to ask, say, d choose k queries. And so for the technique I just described, n would need to be much bigger than d choose k over epsilon.
But
But
then why would you create the synthetic database instead of just keeping all the answers?
Because it turns out, so a synthetic database, it turns out, can actually be much smaller. So if you want
What is
to,
your example for the moment?
Not with the result that you mentioned earlier, but with a different result.
right, so the size of n that I required in the previous result is in order to get to protect privacy. It's not true that you need a linear number of samples and the number of queries to just get convergence to the mean, right? So I can take few samples. I can take a number of samples logarithmic in the number of queries of interest, and I'll get that they're all alpha accurate. The problem with the previous mechanism is that I won't be able to protect privacy if I just do that. So this is actually sort of an old notion in statistics. This has been around since the early 90s. In fact, they even almost use this as a definition of privacy. If you have a synthetic database, then it must be private. But it was sort of introduced to the CS literature in the work of Dwork et al. A few years ago, where they sort of took it as a goal in itself. So they showed how to take these noisy answers like I described and construct a synthetic database out of them. So it doesn't actually get you any improvement in accuracy or the necessary size of the sample, but it can produce a synthetic database, which is a smaller, more compact object for carrying around all these answers. But their algorithm is runs in time exponential in D, which is going to be prohibitive for large studies. So this is interesting, but perhaps even more interesting is that you can actually use synthetic databases as a tool for getting more accurate answers with a fixed size database. So you can use it as a way of correlating the noise that you give to give better accuracy. And that was first observed in the work of Blum, Ligett, and Roth. I'm not going to describe their algorithm, but I want to sort of describe some basic properties. So they show how to use this very general family of distributions that guarantees differential privacy, known as the exponential mechanism, which was introduced by McSherry and Talwar. And they show how to use this to produce a synthetic database that's small and is differentially private and is actually very accurate, even when n is sort of modest. So in particular, what I want to just say is sort of qualitatively, the amount of noise, so the accuracy parameter, is degrading logarithmically with the number of queries. It's important for large families of queries, and it's still also going to 0 with n. So you can, for a fixed number of attributes d and a set of queries m, you can choose n much smaller. But again, their algorithm is not efficient. It requires essentially sampling from the space of synthetic databases, which can be quite large. Okay, very good. So just a quick summary of what's known. So I talked just a little bit about this sort of interactive mechanism where we add independent noise. And then it showed us that you can get, with synthetic data, we know how to produce these summarizations that give accuracy degrading more like the logarithm of the number of queries. And just one more sort of qualitative point. In all these results, as n grows large, so maybe it has to grow very large, but there's something we can set n to that gives us arbitrary accuracy. And in particular, in the results I'm going to present, in our results, we'll show that an efficient algorithm is actually going to have some fixed lower bound on the amount of noise it can provide. So there won't be any realistic choice of n. Maybe you'll see. There won't really be any choice of n where you can get arbitrary accuracy, which sort of breaks statistics. I mean, sort of the way people do statistics is you should be able to get arbitrarily good accuracy as n grows large. And also, qualitatively, when I say that these algorithms are inefficient, I mean that they run in time exponential in the number of attributes in the database. And we're going to show that that's inherent. So what are these results? So essentially, these results, at a very high level, show that generating these synthetic databases that are private and accurate is as hard as forging digital signatures. And so it's going to build on an earlier result of Dwork, Naor, Reingold, Roth, Blum, and Vadhan, in which they construct a family of databases for which no sanitizer that's efficient and produces a synthetic database can preserve a particular type of query, although it's a very unnatural type of query. It's not one that we particularly want to do. So after this result, you might have thought by sort of maybe analogy to like computational learning theory, where with cryptography there are certain kind of unnatural types of things you can't learn, but many natural things are learnable in, say, the PAC model. But what our work shows is that this is actually not true. So an efficient algorithm, so any algorithm that produces a synthetic database that's accurate even for the two literal conjunctions. So this really rules out any large family that we'd like to talk about. It's infeasible to construct such a thing. So producing a new database that even preserves the means and correlations of the original database is infeasible. And so what I'm going to do, I'm actually going to start by presenting the result of Dwork et al. Because it's essentially a building block for ours. We sort of start with their construction. And I'm going to explain at sort of heuristic level digital signatures and PCPs along the way. So a digital signature, this is like a very simple picture of a digital signature. You have some security parameter. You ask for a pair of keys. You get a private key, which I denote SK, a private signing key, and a public verifying key. This specifies two algorithms, sign the signing key, verify the verifying key. You give the signature algorithm a message. It produces a pair M and sigma, which is the message and a signature. And if you produced M and sigma in this way, then the verification algorithm will accept. And the security property we want out of these digital signatures is that they're unforgeable. So imagine that there's some forger that runs in time, that runs in polynomial time. Polynomial is in the security parameter. And it doesn't get to see the secret key, but it gets to have black box access to the signature algorithm. And it sends messages, and it gets to see signatures, and it gets to see some polynomial number of them. And at the end of this game, it has to produce a new message signature pair. And the security property says that with very high probability, the verifier won't accept this new message signature pair. So this is fairly standard. There's one small additional property that is not quite standard, which is that we require that the forger can't even produce a new signature for an existing message. This is called strongly unforgeable, or sometimes super secure. In terms of strength of assumption, these can be their standard transformations from standard signature schemes to these types of signature schemes.
You mean existing message being one of M1 up to MT, or what does existing?
Yes, right. So he's seen signatures of T messages, and he can't even produce a new signature for one of those T messages.
So is in general, does this guy have a memory? Because otherwise, how would the verifier know? I mean,
yes. So we're playing a game. So so he might. Maybe the verifier does accept, but there's someone else watching to make sure that the forger hasn't submitted an old query. So
the verifier accepts one of the messages.
Yes. Right. Yeah. Sorry. So my picture maybe doesn't quite cover that case, but.
I don't understand what old message means, because obviously it can't be one of these old messages M1 up to MT.
That's what he's saying.
That's what I'm saying.
He's saying it can be.
There's
It's
just-
not able
right.
to produce
Yeah.
a fake signature to one of the old
So what I'm trying to say in this little picture is that this whole I guess this is not right. The message and the signature must be new. So ordinarily it would be okay to produce, let's say, a new signature that signs M1.
So the correct scheme is being verified by an independent
Yes, right.
not on the board.
Yes, sorry. There's someone on the board actually enforcing this condition that this is a new message signature pair. So he could trivially produce a valid message signature pair, but someone will notice that this is, he's not really doing what we want. So the observation is that if this forger had access to a polynomial-time sanitizer, then it would be able to forge signatures. So you think of this. So think of the verification circuit with the verification key as defining a counting query. And now imagine constructing a database in this way. You generate some random data for each individual independently, and you sign it with the signing key. And by construction, the answer of to this counting query on the database is 1. Every person is a valid message signature pair under that key pair. Now imagine you fed this into an efficient sanitizer that produced a synthetic database and was alpha accurate. Let's just I'll specify alpha as a half. So by accuracy, this new synthetic database must be such that half the rows are valid message signature pairs. But in particular, I really could have chosen alpha to be anything smaller than 1. At least one of the rows must be. So in particular, there's some row that's a valid message signature pair. And there's 2 possible cases. Either it's one of the original valid message signature pairs, in which case we violated the privacy of an individual. And the other case is that it's new, and meaning it's violated unforgeability.
I don't know which pair. I didn't know which individual it is, right? I only know the existing individual with this property, so that doesn't necessarily violate my privacy.
Yes. Right. So Right. So if you think about differential privacy, in particular, if the person who had this message, if the person whose message signature pair was, didn't participate in the database, then you shouldn't be able to produce his data at all. So it can't be differentially private because this is not something that I could have produced with any significant probability if that person opted out of the database. But it's true that I don't. I know there exists such a person. I don't actually know who it is, but this is maybe philosophically. I still think this is a problem to be able to say, there was someone in the database with exactly this data. No, I think sort of any reasonable privacy definition should not allow that.
Wait, but M is just your name, right, in your example. So you can.
No, it's all your data. M is all your data.
It's all your data.
Oh, so you can think of it as including your name,
Yeah.
right?
Yes, you can. Yes, you can think of it as including your name. But it might not. So we can maybe say it doesn't exactly include your name.
Identifying characteristics and not the name.
Yes.
That's already
Right.
a privacy violation.
Yes.
Or should be a privacy violation.
Right. So just to summarize, so the class of queries is essentially just this verification circuit or query or predicate, and any efficient sanitizer that outputs really any sort of accurate.
So either
sure.
it's not differential private, so how do
Or it violates this unforgeability.
Oh, okay. Sorry. Yeah. So, right. So case 1 is that it's not private, meaning that it's someone in the database. Case 2 is that we forged a new message signature pair. So that essentially that can't happen if the sanitizer is efficient. So the contradiction says that the sanitizer can't be efficient. So this is a class of queries that we can't produce an accurate synthetic database for.
Why does the synthetic database have to have the signatures appended to it?
Because the synthetic database has to have the same type of data. So really the rows of this data are really just bit strings. But they have a fixed length, and they have to have this. In the original database, they have this property that if I split them into whatever length is the message and whatever length is the signature, I can run them through the verification circuit. All we really require of the synthetic database is that the length of the messages is the same and that they're bit strings.
So the synthetic database should look like real database.
Why? So that's why
That's the definition of
But she's
synthetic
asking,
Yes,
why can't you drop the signature and say it looks like it without the signature?
Essentially, my question is, why does the synthesized database need to look like the original database? Why can't it look totally different?
Certain queries won't even make sense if it looks totally different, right? So what I'm really interested in as a statistician is not verifying digital signatures. I'm interested in the marginal distributions of all the columns. So if you wanted to produce a synthetic database that dropped the signature part, that would be like saying there's a bunch of attributes that I just throw out the data for, which wouldn't.
Potentially there are other ways to do this.
Yes.
This is a lower bound specifically for algorithms that do output something that looks
Yes.
like
So you need to assume that you also have this definition of sometimes called the universe, right? That
Yes.
each line has to come from this huge set of possible
Yes. Right.
options, and that set you choose it to be all things that look like a message and a valid signature for it. And therefore, it has to be also the case for the sanitized database, right?
Yes, but I don't actually need to assume that it has this message signature structure, because really a message signature is just a string of bits. So in this case, I can just assume that it's some number of binary attributes. You can choose in your query to sort of parse this as a message and signature, but I can take any bit string and I can choose to interpret it as a message that with a signature.
But then the question is valid, right? Why can't you just...
No, because it has to be the same length. I can always...
Always input to the query, which is the verified. That's it.
So her question is kind of a deeper question, which is why can't you construct? Is there a way of constructing synthetic databases which have entries of different length than the original database? But that's a totally different question.
I don't think it's a
That's a total, right?
I actually agree with Yael. I don't see why in that case, if your synthetic database can be arbitrary bit strings, then why would it violate unforgeability? Maybe it's just bit lengths that won't verify.
But it's bit strings of a fixed length. So
John, maybe you should just remind what is the definition of accuracy.
Right. Sorry. So the accuracy. So the accuracy is with respect to a particular query, right? So it says, so the property we want of the synthetic database is that the number of, so the synthetic database by definition is the same length. It's bit strings of the same length as the original database. And the property we require for accuracy is that this particular query gives essentially the same answer. And that particular query is take your d bit string, parse it as a message and a signature, and apply the verifier.
Percentage of things that...
Right. So it's not... Yes, right. So it requires that the strings can be parsed in this way and would yield valid signatures. And so yes, so it's true, as Aaron pointed out, that this result applies to this type of summarization. It does not apply to arbitrary ways of summarizing the data. The idea of just dropping the signature part of it doesn't really correspond to a good summarization in some sense, because it's like ignoring half the attributes or something like that. Okay, so just...
Make up attributes?
You could make up attributes. I mean...
It's hard to make it accurate.
Right, I mean, in theory, you could make up attributes, yes. So as long as it sort of contains the attributes you're interested in as a subset, then it wouldn't avoid this. But I mean, yes, you can sort of imagine arbitrarily complicated ways of summarizing the data, and I neither know how to produce them nor how to roll them out. So, of course, at least if we're not worried about computation time, then the mechanism of BLR would be able to produce an accurate synthetic database for the setting. But of course, we've seen this is sort of not a natural query. It's not one that any statistician is particularly interested in. There's no reason to think that the US Census contains digital signatures. Very strange. So in our work, which we'll get to now, we can extend this to show that you can't produce a synthetic database, or it's infeasible to produce a synthetic database that preserves the answers to all of the two literal conjunction queries. And to do that, I'm just going to sort of quickly introduce the machinery of probabilistically checkable proofs. And I'm introducing it partly just for concreteness, and also because we consider them in a slightly different way that adds a small twist to the game. So this is a very high-level picture. So you have of a PCP as a CARP reduction. You have some efficient algorithm, which I call the reduction, that takes a circuit and produces a 3CNF formula. And it has the property that if the circuit you give it is satisfiable, then the 3CNF formula is also satisfiable. But it also creates this approximation gap. If the circuit is unsatisfiable, then the 3CNF formula you produce can't even be approximately satisfied. There won't be a satisfying assignment to significantly more than 7/8 of the clauses. This is pretty standard. So there's nothing exactly special about 3CNF, although it makes the argument a little simpler. So I'm going to focus on 3CNF, and the privacy implication you're going to get is for 3 literal conjunctions, but I'll quickly explain how it can be applied to 2 as well. So what do we need that's different? So intuitively what we're going to be doing is we're going to be trying to actually produce a database full of satisfying assignments to some 3CNF, and then we're going to have to try to decode to some particular type of satisfying assignment that produces a digital signature. So what that means is we need to view the PCP theorem as a reduction between search problems. So I'm going to explain sort of schematically a PCP as a Levin reduction. So there's now 3 algorithms. There's the reduction, which works as I said, and there's an encoder and a decoder. And the encoder, so we start the same way. You start with the circuit, we apply the reduction, you get a 3CNF formula. Now, the encoder is going to take satisfying assignments to the circuit and a description of the circuit, and it's going to produce an assignment to the variables of the 3CNF that satisfies every clause. And the decoder is going to work the other way. It's going to take any assignment to the 3CNF formula that satisfies just better than 7/8 of the clauses, and it's going to produce a satisfying assignment to the circuit. So this is not maybe the way PCPs are usually looked at, but it is actually known that standard PCP constructions work this way. So these exist. So how are we going to apply this? You start with the construction of a hard-to-sanitize database from Dwork et al., which contains these message signature pairs. And now what these really are is they're satisfying assignments to the verification circuit. So we're going to apply the reduction and get a 3CNF formula, and we're going to encode each of the rows as a satisfying assignment to this 3CNF formula. And now to just make sure the mapping between sort of, accounting queries and this 3CNF formula is clear. So each of the clauses of the 3CNF is a 3 literal disjunction. And being slightly informal, of course, 3 literal disjunctions are just the negation of 3 literal conjunctions. So for accuracy, preserving all of these is the same. So the property you get in the new database, which contains these assignments, is that for every one of these queries specified by the clauses of the reduction, the answer to the query on this database is 1. So the answer is 1. Now again, we have some efficient sanitizer that preserves the accuracy of all the 3 literal conjunctions. And what you get is that for every one of the clauses of the 3CNF, you get that the answer on this new database is 1 minus alpha. So let's think of alpha as being something like 0.1. So the answer of every one of these queries on the new database is like 0.9. In particular, there has to be some row that satisfies 90% of the clauses.
In this case, now we have many queries?
Yes, so there's many queries. So I'm thinking of this. So what the sanitizer is supposed to do is it's supposed to preserve the accuracy of all 3 literal conjunctions or disjunctions, either. But in particular, it preserves the accuracy of the ones in the 3CNF clause, or the 3CNF formula. So that means I can find a row in this new database that satisfies 90% of the clauses. And now I apply the decoder. I actually should give the decoder the verification circuit, but I take this row and I PCP decode it. And I'm going to get a message signature pair. And by the property of the decoder, which says that since 90% of the clauses are satisfied by this row, I get a satisfying assignment to the circuit, which is a valid message signature pair. And again, there's 2 cases. So either this is one of the message signature pairs that I encoded, and I violated the privacy of that. I can re-encode it to find that person's data. Or, of course, it's not, in which case I forged a signature. Everyone clear on the construction?
So can you how did you use the previous unnatural counterexample?
So we use the same construction. So we start with this database where the circuit we're interested in is the verification circuit, and the satisfying assignments are these message signature pairs. but then we sort of encoded them in a way that's robust to the noise introduced in the synthetic database, and also allows them to be sort of checked locally using these kind of simple natural queries. So we kind of exploit this connection between the local checking property of PCPs and kind of natural statistical queries, which just happens to...
So in other words, this PCP allowed you to produce a unnatural query which you think of as a large satisfying problem into
Yes.
3 CNF which you think as a natural.
Yes, exactly.
Several instances.
Right, local.
Yes, exactly. So yeah, just checking a collection of very local, simple constraints.
So if your alpha had been like really tiny, like exponentially small, inverse, polynomially small, you don't need PCPs.
Yes.
And but to get to a constant alpha, you need a PCP.
Yes, right, to get to a constant alpha. And so I made the point when I summarized the positive results that, you know, depending on the dependence on the queries changes, but in all the cases, as n grows large, you get better accuracy. And in particular, if you use these PCPs, then there's some constant threshold, which in particular for 3 literal conjunctions is even like a, you know, pretty concerning one, like 10% accuracy, that you can't go below. I mean, if you made the database have exponentially many rows, then there's no reason you can't forge a signature by looking at all of them. But for polynomial number of rows, you can't go below like 10% accuracy.
So where does 901 come in?
What?
Where does 901 come in?
Oh, the 801? Oh, sorry, that was just, this has just become a running joke. Salil and Cynthia have a calculation for what epsilon should be to ensure privacy over your lifetime, and they think of it as 801, 1 over 801. And sorry, it has nothing to do with our results. But that's good. Nice light refrain. So just to sort of summarize, so if the class of queries is disjunctions of 3 literals or conjunctions of 3 literals, then any efficient sanitizer that's just better than 1/8 accurate preserves the answers up to 1/8 can't be private. And just to compare this with the positive results, so there exists an efficient sanitizer without synthetic data that's reasonably accurate for 3 literal conjunctions. So this is such a simple class that we don't even really need one of these summaries to get reasonable results. But of course, this rules out, you know, the larger families we'd like to get. And also this, you know, to contrast with what we can achieve inefficiently, the BLR mechanism would actually be able to produce synthetic data that preserves this class.
So your DQ would have been trivial in this first bullet, for instance. I just publish all the results of all 3 conjunctions on litters.
Yeah, oh, sorry, I meant to change that to avoid. So you can do slightly better. You can get square root of the number of queries using independent noise. But in general, it's, you know, for k that's not constant in D, it's going to have the same sort of qualitative behavior.
So 3 is not the same 3 as if it had been disjunctions of k literals.
Then it would be D to the k over 2. So yeah, so sorry, the 3 halves is maybe not meant to be. The 3 is the more interesting part, I guess. Just in fact, so we sort of mentioned that this doesn't just rule out differential privacy. This really contrasts the sort of very, very strong things that we can achieve consistent with differential privacy. Any
reasonable notion of privacy? So I'm not understanding why this rules out any reasonable notion.
So maybe it's just, you know, notions that are reasonable to me, but I would argue that that if you have an algorithm that allows some adversary to come and reconstruct one person's entire record in the database, this should not be considered private under any reasonable definition. I mean,
you really think about the number of attributes is huge. It's like almost the size of the population, which is, I'm not sure that this is a natural assumption.
So I mean,
It all contains your name and your social
No,
security.
But if there are only 10 attributes per
Right.
person and there are a billion people,
Right, but-
you can't do this.
right, but then I can also, I can afford to run in time 2 to the 10, right? So yes, so I mean, this result rules out. So what we're saying is that the running time of these sanitizers has to be exponential in the number of attributes you collect. Yes, if it's 15, then you're not worried about the growth in the number of attributes.
Fine, right? So I can particular store the names of everybody that sort of just log in, and I can sort of
enter bank
Their names of bank accounts.
I mean, you can add, I mean, how much
Sure.
Yes, but maybe not your bank account balance history.
Right, and also, I mean, these are just binary attributes, right? So in a real, I mean, in a real database, if you have 80 bits of information about a person, that's not really very much. I mean, so.
I guess that's true.
But you're not actually reconstructing the original database. You're reconstructing the signatures which produce the database.
But I can, the encoder is deterministic, so I can, if I produce the signature that was encoded to produce your row of data, then I can re-encode it to produce your row of data. So I can actually produce the row of the database. Okay, so I guess this is trying to be more editorial than I thought, but that's good. So also, I mentioned, so this, we can generalize this argument pretty straightforwardly to 2 literal conjunctions or 3 literal XORs, which are also simple, natural types of queries. Just sketch it very quickly. This shouldn't come as much surprise, but you can have PCPs that reduce to other types of constraint satisfaction problems. The argument is just epsilon more complicated because you may not have perfect completeness. It may not be that every query. I think this is fairly well understood. So in the last, I guess, 5 minutes or so before I have to wrap up. So essentially, yes, of course.
So in your result, but also in the previous result that you're relying on, in your result, the queries are very, very natural. But the database,
Yes.
I mean, essentially what your database, or their database, I as a person, cannot efficiently compute my own entries.
That's true.
So what's not natural is the database itself.
Yes, so that's definitely true. There is some recent work by Hart and Roth Blum where they consider a particular sort of notion of data coming from a natural distribution, and they show that you actually can do this type of sanitization. I don't have an opinion on whether this captures natural distributions we think of. So, in particular,
No, you wouldn't be able to generate your social security number. Who knows?
I wouldn't be able to generate my social security or something.
Possibly, right? I mean, who knows what goes into the...
I mean, but at the same time, I mean, just having a database
I don't
that...
know how to do it personally, but I can't imagine these guys are running some exponential computation every time someone needs a social security number.
Of course they are. Giving up money.
So essentially, here's my question. Here's my question.
The data is not exponentially, I mean, digital signatures you produce efficiently. They're just,
If you know a secret.
if you know the,
Signing key.
so they could be,
Yeah.
it is conceivable that
Right.
you would set up a system to produce social security numbers as digital signatures or something.
Right.
It should be, right? I mean, it should not be forgeable, I guess. I mean, if I can forge social security numbers, then...
unfortunately you can.
So here's my question. If the database has the property that each person's database, data entries are efficiently computable. Okay, if I give you a database with a property that for each entry it's efficiently computable. It's a some distribution, but it's efficiently computable.
Okay.
Do you have any intuition, or have you thought about the problem whether you get a positive or negative? I mean.
So I mean, I'm not sure efficiently computable is the right thing, since, I mean, if you have the signing key, then you can efficiently compute the distribution on databases that we construct. Right? I mean, you can generate messages, you can sign them efficiently, you can PCP encode them, but they're not.
You don't know the secret key. If you knew the secret key, then you wouldn't get a contradiction.
Yeah,
So
you don't know whether you smoke or not. That's not a data that's computable. You happen to know the answer to this question, but I don't know. The data is something.
Right.
social security number. The other stuff about you, do you have lung cancer, do you smoke, do you drink alcohol? These are facts. They're not computable or not. They're just facts.
Well, they might be computable if I knew your DNA.
So that's a big philosophical statement. So in some sense, what the result relies on is the fact that I can't sample from the distribution of people who have similar properties. So I can't generate new people who look roughly like the original people up to the marginal distribution of every two variables. So this is a particular type of bizarre database where you can sort of provably say that this can't happen, and the results are very bad if you try. But maybe like more intuitively, you sort of identify this as being kind of the barrier to generating synthetic data using kind of the techniques we know how to do. Is that what we don't know how to do is we don't know how to sample new people who look like the original people in the database in a way that doesn't depend too much on them. So this is my high-level explanation for why this might apply. But yes, so I mean there are some types of data, of distributions on data, where you can produce summaries. And that's, I think, one important area to go for. And then another thing is to understand what types of sort of compact summaries we can produce. So I see on the clock it's 2:30, so I may have to wrap up, but if everybody wants me to go on for another couple minutes. So in our paper, we sort of identify one type of way to relax the synthetic data requirement to a different type of summary. And there's a particular type of summary that we're trying to capture that I'll explain in a moment. So the idea is that when you have the synthetic data, you have a counting query which essentially specifies just a vector of yeses or nos. Does the first person satisfy this predicate? Does the second? So on and so forth. And when you evaluate this as a database, you just look for the average number of, you look for the fraction of people who satisfy the predicate. So what if you had something where you still produce a database from the same universe and you still apply the predicate to each person individually, but the way you get your answer is you apply some function to the vector that specifies who answered correctly. So I think what was sort of the motivation for this is that you might want to consider something like you have a collection of databases and you evaluate each of them and then you take the median answer for each query. So this was used in the work of Dwork, Roth, Blum, and Vadhan. But you can imagine other types. So the question is whether you can sort of overcome the barrier of synthetic data this way. And in general, the answer is sort of yes and no. So in particular, if F does what I described, it sort of splits the database into a bunch of smaller databases, computes the answer on each one, and then takes the median answer, which may, for each query, be a different database. Then no. So with slightly weaker parameters, this also runs into this signature forging argument. If F is any monotone symmetric function, the same thing happens, but again with weaker parameters. Also, if you have a CSP that's very hard to approximate in the sense that even producing an assignment that satisfies any inverse polynomial fraction of clauses, then you're really hosed with this approach. In all cases, the lower bounds work on the same sort of principle. You force the sanitizer to produce a row that can be PCP decoded. It didn't make it on the slide, but we actually did identify one setting where you can produce these summaries, at least for constant number, for any sort of constant arity predicate, and the type of evaluator F we consider is just an affine function of the answer. So you get some synthetic database where the answer to every query is very small, and then you multiply it and add something. But I don't want to go into the exact definition. I guess in some sense the reason we looked at this is because there's these positive results that had these the summary they produced was a collection of databases, and we wanted to show that the same sorts of complexity obstacles arise. So I'm just going to wrap up. So what we talked about is that there's this very strong, robust notion of privacy, and it's possible to get really surprisingly accurate private summarizations of databases consistent with this. But for even some very simple natural classes of functionality, it's infeasible to produce these types of summaries. And so I think that we have to look hard for sort of new types of summarizations of data that can support statistics, or as Yael suggested, look at sort of more natural distributions on data to encourage everyone to do that. He's there. Thank you.
So you did mention some kind of summarization, but maybe Aaron, you mentioned some kind of summarizations are possible for the same class of queries, or?
So in this paper we have a type of summarization which is possible for any family of constant arity predicates, and but sort of what's maybe unsatisfying as a positive result is that it's not any more accurate or compact than answering queries using just the noisy counts method I described. So if you actually wanted synthetic data just so that you could, for instance, feed it into some algorithm, then maybe this is helpful, but it doesn't really allow you to do anything that we sort of maybe couldn't do. It just shows that there's sort of a way to get around the synthetic data barrier that's not too different from synthetic data.
Even if it's not, like you don't know if it's hard in the average case, is there a way that you can test a database to see if it, like, so I use some encoding and then I want to test to see if it's secure or if it violates privacy. So maybe I don't know which databases I know which databases it works on, even though I don't know if it works on a large number or a small number.
Possibly, right? So if you could, okay, so I mean it's, right. So in some sense, if you had some, so like you could, so ideally, right, you have some property of the data that would say, whether or not you have some algorithm, and you identify some property of the data that would say, if the data comes from this has this property, then my algorithm will produce accurate answers. One, small catch is you'd want to be able to test that the database satisfies this property without leaking information, but maybe you can do that. As for running the sanitizer and then trying to violate someone's privacy, I mean it may be possible in the sense that you can try decoding all of the rows and seeing if any of them match, but at least will that work? I guess I don't have a great answer to that. Whether you can do it like ex post after running the sanitizer.
Now, let me ask a different question. So, if factoring turned out to be polynomial, then you could maybe still do.
Yes. Yes. So at least in our results, if one-way functions don't exist, then it's entirely possible that we can produce accurate synthetic data. But we'd have bigger problems, right?
So is there a way to get it under weaker assumptions? I mean, under sort of the randomization assumptions, because essentially the forger you create is just the sanitizer and then some fixed complexity. So the complexity of the forger is essentially the complexity of the sanitizer, which is given beforehand. So maybe you can choose, like once you know the complexity of the sanitizer, you can somehow use this sort of assumptions to create something that acts as signatures with respect to.
So it's maybe possible. So actually, I think it would actually be really interesting to know if you can get these results from worst case assumptions, because so in learning theory, there's kind of two types of hardness results. There's sort of hardness of proper learning, or hardness of learning with a specific representation, and there are these representation independent learning problems. And the reason why we have trouble proving representation independent sanitization bounds is because we've already used kind of both techniques just to get this result. So if it would be maybe encouraging if you could get these types of things with worst case type assumptions, and then sort of free up cryptography to get representation independent results. And I should say there are representation-independent hardness of sanitization results for cryptographic queries in the Dwork et al. Paper that we built on, but they don't. This technique doesn't necessarily cover.
Okay, thank you.